morning session of whatever session name it is. It also means that you've decided to either stay in Lake Placid or brave the weather. Courageous choices. I guess so I'm both moderating and giving the first presentation, so my speech for other presenters is we are recording all the talks to talk to Susan. If you do not want your talk uploaded online, I guess and for other presenters that we are doing the timings from the 15-minute mark, so you'll get the 5-minute warning at the 10-minute mark. All good? Cool. I guess I will introduce myself. So I am Kimberly Fitzpatrick. I am a PhD student at Cornell University, and I am super excited on this very snowy morning to be sharing with you all my work on predator-prey population dynamics for Chinook salmon and alewife in Lake Ontario. I do want to take a second to acknowledge all of my wonderful co-authors who are on this project, who without this project would not be where it is, and have given some great feedback and vastly improved this modeling project. So for those of you who are not familiar with the Lake Ontario system, Chinook salmon and alewife, why are we even doing these fish? So Chinook salmon is the #1 recreational fishery in Lake Ontario. So it means it's important for local economies, local culture, local ecosystem, everything. So it makes up about 50% of all the fishing trips that go out each year. And kind of the one downside with Chinook salmon is that they only eat one thing. So they only eat alewife. It's their entirety of their diet for all intents and purposes. If you really want the number, it's like 99.99999, repeating fairly far out. And this wouldn't be so much of a problem to some degree, except for alewife, and it works when there are lots of alewife in the lake, super great. Alewife currently make up about 90% of the pelagic prey fish biomass in Lake Ontario. And the other problem is that, in addition to Chinook salmon, they feed just about every other sport fish in the lake. Sure, you can think of one that does not fall in that category, but all the Pacific salmonids, lake trout, all like to eat this guy for better or worse. And this makes managing for Chinook salmon a bit difficult. So really to manage for Chinook salmon, because their entire diet depends on alewife, you really need to think about this predator-prey balance. So how many predators are either being stocked with other sources going into the lake, and how does that compare to how much available prey biomass there is? And really the only way to kind of balance that equation out is via stocking, which I'll leave up to Steve with that important job. And this works pretty well. We've had Chinook salmon in the lake and alewife for about 50 years. It's been a dominant Chinook salmon alewife lake, but there are some threats to this potential predator-prey balance. Most importantly, or probably most notably, is that we control all the stocked fish that go in the lake, but not the other side of the coin, so not the wildly recruited predators within the lake. So I took this figure from Dan Bishop, but this is an index of wild salmon recruitment over time in the Salmon River. And at the very least, you can see that it's pretty variable over time, which can cause problems with trying to have a nice stable system. And a sneak peek to the rest of this talk, perhaps increasing in this time period. So we might have this system where at least variable, if not increasing, predators are in the lake. And then on the other side, we've had in recent years, I stole this picture from Wild, we've had kind of poor or low alewife recruitment over time. So this is an index of age 1 alewife abundance over time. And particularly in these 2 years here, 2013 and 2014 cohorts of alewife were notably low, with 2014 being the lowest on record. So we've got a system where we've got a lot of predators coming into the system, and perhaps an interesting or low amount of prey, which is concerning. And then kind of to top all of this off, I want to keep in mind for all of this, I'm going to mostly focus on this predator-prey relationship, but lower trophic levels are important. We know the lake isn't this stable, static state over time. And one of the things that happened with the Lake Huron crash of alewife and Chinook is that they think that the declining nutrients and changes of lower trophic level dynamics kind of created this bottom-up impact on alewife, and then they kind of got slammed from the top down by that wild recruitment of Chinook salmon. So that squeeze is something to keep in mind. So, maybe. Oh no. So this project had a couple of key objectives, and what we wanted to do was we wanted to create a tool to get at the management of, to help inform the management of Chinook salmon and alewife within the lake. And sort of the big key overarching objective was that we wanted to first estimate the dynamics of Chinook salmon and alewife, but we didn't want to just estimate them separately from each other because they've got that really tightly coupled relationship with predator-prey. We wanted to expand it to incorporate predator-prey interactions, which is not particularly common in traditional fisheries models, is that they usually focus on a single species at a time. And then kind of, again, this overall thing about not only what's been going on in the lake up till now, but maybe creating a pathway to start in a structure to think about and sort of the statistical framework, future decision makings and what's going to happen in the lake, what's upcoming in fishery, and maintaining that balance between predator and prey. So what did we do? We created a model. I'm not at 8:30 in the morning going to show you a bunch of equations. You guys can all breathe a sigh of relief. But I am going to talk to you about this simple conceptual model of the model. And for those of you who are familiar with fisheries models, this is technically falls into the class of a multi-species statistical catch and age model. But now I'm going to break it down for us, but all of us, myself included. But it kind of breaks down into 4 main submodels, 2 of which are population dynamics models, so models controlling abundance, mortality, biomass, all of these sorts of things. And one of those is for Chinook salmon, and one of those is for alewife, and that includes also mortality from other predators for alewife. But the really interesting and really cool part about this model is that it also includes those interactions. So the first one goes sort of the impact of predator on prey, which we model using a functional response relationship for predation, so that predation of alewife changes with both predator and prey abundance within the lake. Similarly, we have a feedback that goes from prey to predator abundance, or prey to predator. So sort of that bottom-up feedbacks are there, and that's focused on Chinook growth. So it's a bioenergetics model, and it means that Chinook weight at age is influenced by how much alewife they can eat, which may seem pretty intuitive, but it's really important to sort of have these feedbacks that are in there and that we can see and that they're physically in our model structure, and that's really important for talking about the relationships between these species. And just to give you a glimpse into the inner workings of this model, maybe, is that all of this we can kind of see glimpses of at the same time. So it might not be exactly an index of the entire lake abundance of Chinook salmon, or it might not tell us exactly what the entire biomass of something is. But we get little glimpses through, say, the Chinook salmon data that we collect each year. So that's your creel surveys, your spawning surveys, indices over time. And we can see sort of how that population might be changing over time. And the same thing with the alewife trawl data is that we use that to look at the same patterns, but with the alewife side of the model. But we can also see sort of these interaction pieces as well. So we can see things like the change in total alewife mortality. And we're not, measuring do you die, do you not die, do you survive. We can't exactly witness all mortalities, but we can look at how fast alewife sort of disappear in the lake. So if we know we have so many age 1s, we should have equal to or less than of age 2s. And you can kind of track that cohort through time. And that's what we're picking up here, is that when that decline is very steep, it may suggest that there are a lot of predators in the lake. And that's part of the key part of this model, is that we're allowed to have time-varying mortality based on predation, which is really cool. And then similarly, we do the same thing for the change in Chinook growth. So we may not be able to see and measure every single individual Chinook, but we were looking at the weight at age 1, the weight at age 2, the weight at age 3, and all of those pieces, and looking at how quickly that changes. If they're eating more alewife, they should be bigger. If they're eating less, they should be smaller. So what I'm going to do in terms of results is I'm going to go back and kind of walk through this conceptual model. And I'm going to show you pieces of output from the model that relate to each of these different kind of circles and submodels within the model. And then I'm going to come back and sort of summarize them all together, so hopefully you can see where some of these feedbacks and interactions are occurring. Maybe. Okay, so first to orient you with this graph is all of my graphs are going to be set up the same. My timeline is on the bottom, 2001 to 2019. My value of interest is on the y-axis. The estimated values are in the colored lines, and one standard deviation is in the shaded area. So this is Chinook abundance over this time period, and what we see is kind of throughout the 2000s, we're doing pretty good, kind of stable, nice. We like stable systems for predator-prey relationships. And then you guys might have noticed this bit here, is that if anyone went out fishing in the last 2 years on Lake Ontario, so 2018, 2019, caught a lot of 2s in 2018, caught a lot of 3s in 2019. It's these fish, is that we think what happened was that we had a large cohort of wild Chinook that came in 2016. And that's what this is picking up on here in our sort of model estimates. And this will feature prominently in some of the other ones, so look for this pattern with the other graphs. So this is, so to kind of move on to more that predation portion of the model, is that we're looking at alewife biomass consumed by Chinook over a given time period. And you can see it somewhat follows what the abundance graph did as well for Chinook, that it's kind of stable, a little high there in the 2000s. And then perhaps very expectedly, when we saw this increase in predators here, we also see an increase in alewife consumption. So perhaps more predation pressure on alewife from Chinook salmon. And then to sort of move over to the alewife portion of the model, these little black triangles are Brian's adult alewife survey numbers, so in biomass. And we kind of see the same thing, that through the 2000s it's stable, but then we sort of get to the later 2000s, that's when those really low cohorts, the really small age 1 cohorts of alewife sort of hit. And then they sort of get this double whammy of this increase in predation pressure from Chinook salmon. And we're at sort of a much lower point than we'd perhaps like to be in the lake. And then sort of my final little graph I'm going to show you in this sort of submodel portion here is Chinook weighted age. This is the weighted age of age 2-year-old Chinook salmon. Little black diamonds are from the New York State DEC Creel. And we see that it's kind of jumps all over the place. If you guys noticed a really high peak in consumption, this correlates very nicely with there, that we had a lot of large Chinooks eating a lot of alewife. Well, when we sort of get to the current years, we've got smaller Chinook, but a lot of them eating alewife. And that's what we see when we sort of put all of these graphs together, is that we start seeing these really common patterns over time. So that stable throughout the 2000s, and then the jump up there, or the decline on the alewife side and the weight side, and the weight and the consumption portion is correlating as well with that sort of peak in the middle there. So to kind of try to put all of this in one figure, and just to summarize a couple of thoughts, is the last graph I want to show you here is relative consumption of alewife by Chinook. So what this is it's all of the alewife that Chinook salmon collectively consume in a given year divided by the biomass of alewife at January 1 of that year, so relative sort of consumption. And what I hope you guys see is that here in the 2000s, it's pretty stable, and then perhaps with that increase in Chinook salmon, it's really taking off. But I do want you to note that here, even though Chinook salmon abundance has gone down at this point in time, we're still seeing a much higher sort of predation pressure that's happening on alewife. And if you take away one thing from this talk at 8:30 in the morning, it's that we are seeing this increased predation pressure on alewife. It is going to have some potentially be impactful on what's going to happen to alewife the next year. And I would like to also remind you that it's not just Chinook salmon that we're considering. that alewife are 90% of our prey biomass for sport fishes, and they are under increased pressure, and this will have impacts on what those species do as well. And then, so I did mention very quickly that we are interested in what this is going to mean for the future. And one of the great things is now that we've kind of built this structure, this model framework for what Chinook salmon and alewife dynamics have looked like in the past, is we're interested in using that to start thinking about future dynamics of these two species together. So what we're working towards is looking at simulating out from this model. So now that we've created and estimated parameters and all of that, we can start really using it to start thinking about what does the next year look like, what does the next 5, 10, how do these interactions really play out? And we can look at things like, because we have this framework, weighted age of Chinook salmon, how do we expect that to change? So like alewife predation, how does that change now that we allow for those feedbacks to happen? And we can look at it under a variety of management scenarios and also different ecological scenarios. So looking at recruitment of alewife. If we have a good year, what does that mean? If we have a bad year, if we have 2 bad years, what does that mean? As well as for Chinook salmon, if we have a lot of wild recruitment, what does that do and what actions may need to be taken? So with that, I will thank all of the wonderful people who have also helped collaborate from this project. Been funded by New York State DEC and all these other wonderful people. Cornell University, USGS, Ontario, MNRF, USGS, MNRF, and DEC have been really instrumental in getting me the data. All of this data that runs this entire model comes from them. And with that, I will take any questions.
We do have a few minutes for questions.
Oh no, Cliff.
So Kimberly, so make a prediction. So alewife, what's going to happen this summer, this next year?
Do I want to make this prediction with Steve?
That's why That's why I'm asking.
I think it is important that we've been making stocking cuts over the last couple of years. I think those will start to play out on the Chinook side and the predation side. We have low spawning stock biomass for alewife, and that's the most concerning piece, and not really understanding